So it's all yours, Martin.
Okay, thanks, Lucas. Thanks, Lucas and Mati, for this invitation to give a talk here. As Lucas said, I'm Martín Lagares. I'm from the University of La Plata, Argentina. And today I will be presenting this work that I did with Johannes Hen and Shunking Zhang in these two papers that I mentioned here. The talk will be about infrared finite observables from geometry. And in particular, I will be discussing the case of the ABJM theory. So let me begin by a quick outline of the talk. I will be starting with a discussion of how can we describe scattering amplitudes using a geometric approach. Then I will comment about how we can construct higher finite observables from this geometric construction. Then I will discuss how we can apply this to the ABJM theory. And finally, I will be giving a prescription of how we can use these higher finite functions to compute what is known as the cusp anomalous dimension of the theory. And then I will conclude and give some possible future directions from this work. So let's start by giving the definition of what's scattering amplitude. I guess all of us here maybe know what's scattering amplitude, but just in case, let's mention that if we have a dispersion process between n incoming particles with momenta p1, p2, and pn, and some internal degree of freedom, r1, r2 to rn, and then we have m outgoing particles with momenta q and internal degrees of freedom w, then the scattering amplitude is defined as the transition amplitude between the initial state and the final state of this scattering process. So as we know, scattering amplitudes are very important objects in quantum field theory, because basically we can obtain what is known as the cross sections of the scattering process from the scattering amplitude, and then this is an observable that is directly measured at the LHC. Amplitudes can be systematically computed from a Feynman diagram expansion. For example, here I gave the expansion for a 4-point amplitude in the 5-cube theory up to 4 loops. But this could be different from theory to theory. But we can already see here that when we go to higher loops, the expansion starts to become more and more difficult. But quite surprisingly, the final result is often very, very simple. For example, let me give this canonical example, which is the Park-Taylor formula, which describes the scattering of n gluons in general Young-Mills theory, and in particular describes what is known as the MHV scattering, which is the maximally helicity violating scattering. So let's consider n gluons with helicity plus, all plus helicities, but we have to include 2 gluons with negative helicity. When we have 2 gluons with negative helicity and all the others with plus helicity, this is known as the MHV amplitude. So to describe...
Martin?
Yes?
Sorry, I have a question.
Yeah, sure.
I always hear the statement that the final scattering amplitude is really simple, but
exactly. Yeah.
And they always show the Park-Taylor formula example, but in other
exactly,
cases, when you have other theories, I don't know, maybe effective field theory. Is it the case? I mean, scattering amplitude is still like simple, or it's only simple in these cases where you have a lot of symmetries and really control over all the particles?
Well, obviously, scattering amplitudes can be difficult also. It's not that every scattering amplitude is simple, but what is quite surprising is that in a lot of cases, the final result for the amplitude is very simple despite the high complexity of the Feynman diagram expansion. But yeah, obviously, it's not that every amplitude is simple. Yes. I don't know if that answers your question, maybe. Or
Yeah, kind of. Thanks.
yeah, there we go. Yeah, please interrupt me anytime you want. Of course. So just give me one sec because I have this. Okay. Okay. So to give the result for the Park-Taylor amplitude, let me introduce what is known as the spinor helicity variables, which are these two spinors here, lambda and lambda tilde, that allow us to parameterize a massless momenta P, P alpha alpha dot. Here, the alpha and alpha dot are indices of SU2 in the fundamental representation. And from this lambda tilde, we can construct Lorentz invariants by simply contracting the spinor helicity variables with these Levi-Civita tensors. And then the Park-Taylor formula tells us that at tree-level, MHB amplitudes are simply given by this formula for the endpoint amplitude. And this is very surprising because this is a very complicated Feynman expansion, Feynman diagram expansion that sums up to this very simple result. So is there a way in which we can understand why and where this simplicity comes from? Well, a very interesting approach to answer this question was given 10 years ago by Arkanemed and Trinka, where they propose that for some theories, scattering amplitudes could be described by what is known as positive geometries. Basically, this proposal tells that amplitudes can be computed as the volumes of these mathematical objects that are the positive geometries. And to be more specific, the amplitudes are related to what is known as the canonical form of the positive geometry. So what is a positive geometry? So to define the concept of positive geometry, let's consider a d-dimensional manifold, so a manifold of d dimensions, with boundaries of all codimensions. And moreover, let's consider a volume form on this manifold that is called the canonical form, such that has logarithmic singularities on each boundary. And what do I mean by logarithmic singularity? Well, I mean that when going to the boundary of the manifold, we have to have a simple pole in the boundary, and we say that the coefficient of this pole is the residue of the canonical form in this boundary. So we say that this pair, the pair formed by the manifold and the volume form, is a positive geometry if every codimension 1 boundary is again a positive geometry whose canonical form is the residue of the canonical form in d dimensions at the boundary, at this codimension 1 boundary. So it's basically a recursive definition, right? But the important thing here is that we have a unique canonical form for each positive geometry with logarithmic singularities on each boundary. So to give an example, let me discuss the case of the n equals 4 Superman-Mills theory, right? So n equals 4 Superman-Mills is a theory in 4 dimensions which has superconformal symmetry. The gauge group is SUM, and we have SU4 R symmetry, right? The Lagrangian is the one that is shown here, but I mean the details of the Lagrangian won't be important in what follows. And let me mention that the theory is believed to be dual to type 2B string theory in ADS 5x5, and this is a famous proposal of Malacena of the ADS-CFT. So how can we describe amplitudes in n equals 4 Superman-Mills using positive geometries? Well, let's consider the MHB amplitude for n equals 4 Superman-Mills, but let's consider the amplitude divided by the tree-level amplitude, right? We will take the integrand, the L loop integrand for this amplitude, which is the cal I here. And what was shown is that this L loop integrand for the amplitude can be obtained as the canonical form of a positive geometry that is known as the L loop amplitude times some normalization factor that is not important. It's not for what follows. So To give the precise definition of the L-loop amplitude heat run, let me give some small introduction to the kinematics of massless particles. So before I defined the spin of helicity variables, and let me introduce now what is known as the dual space coordinates, which is basically in a scattering process. Let's take two consecutive momenta. Well, let's take the difference of these two consecutive momenta, and this allows us to define these coordinates that are known as the dual space coordinates. In terms of the dual space coordinates and the spin of helicity variables, we can define now what are known as the momentum twistor variables, which is basically this four-component element, where the first two components are the lambda spinor helicity variable, and the last two components are these mu spinors that are defined by these relations here, which are known as the incidence relations. So why do we care to work with momentum twistors? Well, one of the reasons is that we can build dual conformal invariants in terms of these momentum twistors. And let me give just a comment of why I'm talking about dual conformal invariant and not conformal invariants. In N equals 4 Superman Mills, besides the conformal invariance that has the theory by itself, amplitudes have also another conformal invariance that is additional to the conformal invariance of the theory, and it's known as the dual conformal invariance of the amplitudes. And a way to see this dual conformal invariance is, let's, for example, consider the integrands for amplitudes in dual conformal space. That is, let's write the integrand for the amplitude in terms of this dual conformal coordinate, dual space coordinates, sorry. The integrands will have a conformal invariance in that notation, and that conformal invariance is the dual conformal invariance of the amplitude. So, well, let me mention here that points in momentum twistor space correspond to lines in dual space, and lines in dual space correspond to points in momentum twistor space. So,
Martin?
Yes.
Sorry, another question.
Yeah, sure.
This conformal invariance is something that is exclusive to the Siembra-Mills theory, or there are a whole family of theories that have this kind of dual.
The dual conformal invariant. Well, it has been shown in N equals 4 Siembra-Mills that it seems that amplitudes at arbitrary number of points have this dual conformal invariance. In ABJM, also we have this dual conformal invariance, and this dual conformal invariance is a consequence. You can see it as a consequence of having a duality between scattering amplitudes and Wilson loops. I will discuss this later, but in N equals 4 Siembra-Mills, you can, it's proposed that an endpoint amplitude at the level of the integrand can be computed. It's dual to some polygonal Wilson loop. I can discuss it later if you want, but basically this duality allows you to understand why amplitudes have this dual conformal invariance, because basically this dual conformal invariance of the amplitudes is the conformal invariance of the Wilson loop that is dual to the amplitude. I hope this answers the question.
Yeah, thank you.
Yeah, you're welcome. So, okay, so let's now introduce the four-particle L-loop amplitude theorem. I'm going to focus on the four-particle case, that's for simplicity, but the construction generalizes to higher points. So let's consider the region in momentum twistor space that is defined by these constraints. So let's impose first that the momentum twistors that correspond to the external particles, that is the momentum twistor 1, 2, 3, and 4, satisfy this positivity constraint. And also, let's impose that for each of the loop momenta, the line in momentum twistor space that corresponds to each loop momenta satisfies these constraints with respect to the external momenta momentum twistor, right? So here Li is the line in momentum twistor space that corresponds to the momentum, the loop momenta I, right? And finally, well, sorry, these two constraints define the one loop amplitude hedron, right? For each loop momenta. Then we want to impose that each pair of loop momenta satisfy this positivity constraint that is shown here. The region in momentum twistor space that is defined by all these constraints is defined as the L loop amplitude hedron, and it's graphically represented by this figure that we have here. Here, each node is a region in momentum twistor space defined by this constraint, the first one, and these two constraints. This is a one loop amplitude hedron. And then each dashed line is a positivity constraint between two loop momenta, right? Okay, so the canonical form of this geometry at L loops will give us the integrand for the L loop amplitude in n equals 4 CP amps. So let me mention some examples of how positive geometries are applied to the description of amplitudes in different theories. As I mentioned before, we have the amplitude hedron for the 4-dimensional n equals 4 CP amps theory. This was the original proposal. Then it was proposed that also for the ABJM theory, as I will mention later, we have an amplitude hedron. There is also a formulation of the amplitude hedron, not in momentum twistor space, but in the spinor helicity space. And this is what is known as the momentum amplitude hedron. This has been done for n equals 4 CP mills and for ABJM. There is also a positive geometry that describes amplitudes in the B-adjoint phi cube theory. This is known as the associahedron at 3 level and allohedron at 1 loop level. And also there is a very interesting application of positive geometries to the description of cosmological correlators. And this is known as the cosmological polytopes. And it was proposed by Kanyamed and Menincasa and Postnikov. So now let me describe how we can use this geometrical construction to describe not the amplitude, but the logarithm of the amplitude. And this will be important for what follows. So let's consider now a negativity constraint between the loop momenta instead of a positivity constraint between the loop momenta. One can show that if you add the canonical form of a negativity constraint between two loop momenta plus the canonical form of a positivity constraint between the two loop momenta, then the geometries factorize into two one loop amplitude hedron geometries. And one can use this relation to show that the logarithm of the canonical form of the L loop amplitude hedron can be decomposed into all possible ways of connecting all possible connected graphs between L nodes at L loops connected by negativity conditions. So this is an expression for the logarithm of the canonical form. And one can show that if we consider now the integrand for the logarithm of the amplitude, then this integrand for the logarithm of the amplitude will be given by the logarithm of the canonical form at L loops, right? Okay. So we have an expression for the logarithm for the integrand of the logarithm of the amplitude in terms of negative geometries. No. So to summarize, the integrand for the amplitude is given by positive geometries, and we can show that the integrand for the logarithm of the amplitude is given by negative geometries. And an interesting consequence of this is that if you take now the integrand for the logarithm of the amplitude at L loops and you perform L-1 loop integrations, that is, you perform all but one of the loop integrations, then the result you can show that is IR finite. That is, all the divergences of the amplitude concentrate in the last loop integration. Moreover, if you consider the dual conformal invariance of the theory, you can show that this integration, these L-1 integrations, will have this structure that is shown here, where we have a kinematic factor overall, and then we have a function of a single cross ratio. So let me stress again that this function is IR finite, and this means that all the divergences concentrate in the last loop integration. And this is very interesting because performing the loop integrations is very often a bottleneck step in the computation of the amplitudes. So learning how to perform the loop integration is very important. And here we have an object that is IR finite, that is, we don't have divergences, and is one loop integration away from the amplitude. This function has been computed perturbatively in N equals 4 p.m. mills, and it has been computed perturbatively up to L equals 4. Moreover, well, as I mentioned, it has been shown to be IR finite and has uniform transcendental weight. That is, the transcendental weight of each term in the coupling expansion is constant. It's uniform, sorry. Also, very interestingly, there is a prescription to compute the Kasparov dimension of the theory in terms of these integrating negative geometries. If we apply a certain function that was constructed to these integrating negative geometries, one can show that one can obtain the Kasparov dimension of the theory from these integrated results. And this was used in N equals 4 p.m. mills and in QCD to compute the full for-loop Kasparov dimension. Moreover, it was shown that the leading singularities of these results, the leading singularities are the rational factors that multiply each transcendental function term in the expansion of these integrated results. That is, let me say it in another words. If you take these integrated negative geometries, you can always expand the result as a sum over transcendental functions that are multiplied by certain rational factors. These rational factors are the leading singularities. And it was shown that these leading singularities are conformally invariant. And also, it was shown that there is a certain duality between these integrated results and all plus Young-Mill amplitudes in pure Young-Mill theory. Moreover, very interestingly, Ahmed, Hen, and Trinka showed that certain subsets of negative geometry graphs can be non-perturbatively summed to all loops. In particular, this was shown for the tree and the ladder diagrams. And the analysis of negative geometries was extended to higher points, not only for 4 points. In the general case, the integrated negative geometries are functions of 3 n-11 cross ratios. And interestingly, this is the same number of variables as in QCD amplitudes. So, yes.
Sorry, a question. What is the cos anomalous dimension?
I will define this later, but
Okay.
it's basically an anomalous dimension that appear in the theory when you renormalize the expectation value of Wilson loops.
Okay.
That is something that appears quite a lot in quantum field theory in very different places.
Yeah, I heard a lot. That's why I wanted to.
Yeah, I will
Yeah.
mention it a bit later. So,
Martin,
yeah, sure.
a quick question. When you speak about leading singularities, I guess they are not the logarithmic singularities. I mean, it's the one that are related with the positive expected to value.
No.
No?
Yeah, it's a good question, but no.
Okay.
They are called singularities, but they are another objects.
Inside that or
yeah, besides the singularities of the geometry.
Okay.
Yeah, I will define it more properly later, these leading singularities.
Okay.
Okay. So yeah, let's see if we can generalize this analysis to other theories, right? A very good candidate to generalize this analysis of n equals 4 supermills is ABJM, given that it's a very close cousin to the n equals 4 supermill theory. So what is the ABJM theory? The ABJM theory is a superconformal field theory in 3 dimensions, not in 4 dimensions. And now the gauge group is UN cross UN, and the R symmetry is still SU4. So the field content of the theory is given in this quiver diagram. We have 2 gauge fields, each one in the adjoint representation of each of the gauge groups. Sorry. And we have 4 scalars in the bifundamental representation of the gauge groups and 4 fermions. And in this case, also the theory is believed to have an allographic dual, which is type 2A string theory in ADS4 times CP3. So, how is the geometric construction for amplitudes in ABJM? Well, this was done in the past years, and it was shown that one can construct an amplitude for ABJM by taking the amplitude of n equals 4 supermills and imposing these symplectic constructions, projections, on the momentum twistor variables, right? So if we take the amplitude of n equals 4 supermills and we impose these constraints, we can obtain the all loop amplitude for ABJM. And this is very interesting because these symplectic projections have a very interesting consequence on the negative geometries of ABJM. We can show that the logarithm of the canonical form in ABJM will be given by an expansion, not only in connected graphs, but also in bipartite graphs. I mean, there is another constraint now on the negative geometry graphs. And this is very important because it implies a very huge reduction on the number of graphs that one has to consider in the expansion of the logarithm of the canonical form. So let me, define what is a bipartite graph. A bipartite graph is a graph in which each node, after you assign a direction in each of the lines, each node should be either a sink or a source, right? So yeah, this is a very important constraint in the negative geometries of ABJM. Well, let me just give.
Sorry, what is
sure.
a sink and source?
So each line should either end or begin in these nodes.
Yeah, but what does it means? What's the difference between that node? That one is you call sink and the other source. I'm not very familiar with that.
For example, this node, the white node, is a sink because you can see that every line that is connected to this node.
Okay, you use that for define
node.
it. Okay, okay. Okay.
Yeah.
You use this to define them. Sorry, I thought you have
No, yeah.
I mean, meaning. Okay.
I mean, basically, what you do first is you assign a direction in each line.
Okay.
And you should be able, if the graph is bipartite, to see that then after assigning the direction to each graph, each node is either assigned a sink or a source.
Okay.
Yeah. So, well, up to 3 loops, the canonical forms are like this, like the ones that are shown here. This is not very important, just to show you the form of the canonical forms. So before performing the integrations, let me introduce what is known as a finite dimensional notation. That is quite useful to work with integrands in ABJM. So, as I mentioned before, ABJM is a theory in 3 dimensions. 3-dimensional Minkowski scales can be embedded into the 5-dimensional icon that is defined here. And why do we care in embedding the 3-dimensional Minkowski space in this icon? Well, because now, if we take a dual conformally invariant expression in 3 dimensions, this will translate into an expression that has Lorentz invariance and scale invariance in 5 dimensions. So it's much more simple to construct dual conformal invariant expressions, because you have to go to 5 dimensions, construct something that is Lorentz and scale invariant, and then this will be conformally invariant when you go back to 3 dimensions. In terms of these 5-dimensional coordinates, you can construct this 5-dimensional Levi-Civita expression constructed with the 5-dimensional Levi-Civita tensor. And well, the measure is basically a measure that gives you the integration over the Lycon. So what happens now in ABJM when we consider the L loop integral for the logarithm of the amplitude, and we perform all but one of the loop integrations over this loop integral for the logarithm of the amplitude? Well, using dual conformal invariance of the amplitudes, we can show that this integration will have this form that is shown here. Basically, we can express the result in terms of 2 functions of the cross ratio now. And let me remark that here the first term is parity even, and the second term is parity odd. So we have a new contribution. The first contribution is quite similar to the one in N=4 super Mills, but this parity odd contribution wasn't there for the 4-particle case in N=4 super Mills. And it's quite similar to what was observed for the 5-particle case in N=4 super Mills. So let's start computing these integrating eddy geometries for the ABJM theory. So from the amplitude we know that the one loop canonical form is the one that is shown here. The specific form, yeah, don't worry if this seems too complicated. Then when you go back to 5-dimensional coordinates, you can see that the integrand for the logarithm of the amplitude at one loop is this that is shown here in terms of 5-dimensional coordinates. And given that we are at one loop for the logarithm of the amplitude, then to obtain the integrated eddy geometry, we don't have to perform any loop integration, because remember that we want to perform L minus 1 loop integrations. So at one loop, this gives us 0 integrations. And from this, we can easily see that the integrated eddy geometries will be given by these functions. The parity even part is 0, and the parity odd part is just this coefficient -2. Then, on one loop, we have to take the 2-loop integrand for the logarithm of the amplitude, which is this one that is here. And we have to perform a 1-loop integration. So we will arbitrarily choose to leave the x5 coordinate frozen, and we will integrate over the x6 coordinate. And this is what is known as a triangle integral, which can be done by Feynman parametrization, and gives us that this 1-loop integration is this result that is shown here. And from this, we read that the integrating eddy geometries are the ones that are shown here. Then at 2 loops, we can also perform the integration by Feynman parametrization. It's a bit more involved, but it can be done by Feynman parametrization. And the result is the one that is shown here. Let me remark that the transcendentality of this result is 2 for each term. And at 3 loops, the integrations are much more non-trivial. We have to take the 4-loop integrand for the logarithm of the amplitude, and we have to perform a 3-loop integration. And a very interesting feature of the 3-loop result is that now we have to consider the first loop of loops diagrams. And what I mean by loop of loops, well, this box diagram, for example, remember that each node here represents a loop. So we have a loop of loops, right? So this makes the computation a bit more non-trivial than in the previous cases. To perform these 3-loop integrals, we used what is known as a method of differential equations. Yeah, given the time, I decided not to include an explanation of this method. This is very well known in the computation of Feynman integrals for scaling amplitudes in dimensional regularization. But basically, we used this method to compute the 3-loop integrals, and we obtained this this result that is shown here. And let's see now that, again, the result at this loop order has transcendentality too in each term. So let me summarize these results. Up to free loop order, we showed that the negative geometries are the ones that are described here. And we can see that there is a pattern in the transcendentality of each term. Basically, the parity even term at 2k plus 1 loop order and the parity odd term at 2k order have transcendental degree 2k. You can ask why this is important. Well, this is important because if you want to perform, for example, a bootstrap computation of these results, it's very important to know the transcendental degree of what you expect to obtain. Then also we observe that if you study these integrated negative geometries in what is known as the Euclidean region, which is the region in which Z is positive in our conventions, then there is also this particular sign pattern for the integrated results at the different loop orders. And again, we hope that this could be useful for a future bootstrap analysis, for example. And this is analogous to what was observed in N equals 4 superior mills for 4 and 5 particles. So let me discuss now what I mentioned before about the leading singularities, how this translates into the ABJM case. So what is a leading singularity? Okay, let's take the integrated result. That is, let's take the result of performing L-1 integrations over the L loop integrand for the logarithm of the amplitude. We can always write this as a sum of transcendental functions, the t's here, multiplied by some rational function, which are the r's here, right? And we say that these rational functions are what we call the leading singularities. Again, knowing the leading singularities is an important feature if you want to perform a bootstrap analysis to compute these functions, right? It's something that you should be able to know beforehand. So very interestingly, in our case, the leading singularities are the ones that are shown here. And we can see that if we take the unintegrating variable, that is the x phi variable, to infinity, then the leading singularities that we obtain in this frame are very simple, are just restricted to be in this set. We have basically 3 possibilities. Well, it's an open question to understand why we have this simple structure for the leading singularities, right? And well, let me now give a discussion about how can we compute what is known as the Kasparov dimension of the theory in terms of these integrating negative geometries. So what is the Kasparov dimension? Okay, let's consider a Wilson loop in the theory with a Lie caps, right? This Wilson loop, when we compute the vacuum expectation value, will have a divergence that cannot be renormalized by a redefinition of the coupling constant of the theory. Instead, we have to introduce a renormalization factor for the expectation value of the Wilson loop. And this factor allows us to define an anomalous dimension as usual in quantum field theory by this formula. And this is what is known as the Kasparov dimension of the field. So the question that we wanted to answer is how can we compute this Kasparov dimension by using the integrated negative geometries. Okay, so let me comment that here the gamma cusp basically describes the UV divergences of the Wilson loop, but using what I mentioned, I will mention now, that is the Wilson loop and scattering amplitude duality. One can see that the gamma cusp also is useful to describe the IR divergences of amplitudes. So to compute the Kasparov dimension using the integrating negative geometries, one has to consider what is known as a Wilson loop scattering amplitude duality, which basically says that at the level of the integrands, the logarithm of the amplitude is dual to the logarithm of the expectation value of the Wilson loop. In N equals 4 super Mills, this is believed to hold for an arbitrary number of particles, but in ABJM, the duality holds for 4 particles, but starts to fail for 6 particles, at least if one considers the standard Wilson loop of ABJM, the bosonic Wilson loop. It is believed that maybe one can construct a supersymmetric Wilson loop that will serve to prove this duality for higher number of particles.
Martin?
So, yes, yeah.
That relation between the scattering amplitude and the Wilson loop,
Yes.
it's all order in perturbation theory?
I mean, it has been proven 2 loops for sure. And yeah, I mean, it's not, there is no proof at all loop order. I mean, it's just basically proving it loop by loop, and then people believe that holds for all loop order.
Okay.
In particular, you can, in equals 4 super Mills, there is an argument that was the original argument given by Maldacena and Aldai to propose this duality at strong coupling by using a T-duality of the ADS phi crosses phi background, which is quite difficult to prove in ABJM. I mean, there is no proof nowadays of this T-duality, and that's what makes also difficult to prove this duality or to discuss this duality in the ABJM theory. Okay.
But in
yeah.
ranging Mills, it's proven for all order, right?
It's not proven, but it's believed to hold.
Okay. Thank you.
Oh, yeah, you're welcome. Okay, so how can we now use this duality to relate the integrated negative geometries to the Kasparov dimension? Well, let me present this formula that is well known from the renormalization theory of light-like Wilson loops, that basically states that the leading singularity, the leading UV divergence of the logarithm of the Wilson loop. This is, sorry, I forgot to mention this. This is a polygonal Wilson loop, right? Where the vertices are located in very precise positions related to the moment of the amplitude, right? This is not an arbitrary Wilson loop. So the logarithm of the expectation value of this polygonal 4-point Wilson loop will be given at the leading for the leading divergence, UV divergence, by the Kasparov dimension at L loops. And then we can use this formula and use the fact that the duality says that the logarithm of this expectation value should be given at the level of the integrands by the logarithm of the amplitude to propose this relation between the integrated negative geometries and the Kasparov dimension. And this tells us then that at L loops, we can compute the integrated, the L loop Kasparov dimension from the L-1 order integrated negative geometries by applying these functionals to the results, to the integrated results. Then it's useful to consider now the value of these functionals, but not over an arbitrary function, but over a power of set, right? Let's put set to the p here and set to the p here. We can compute that using Mellin-Barnes, the Mellin-Barnes formula. And what we obtain is this formula that is shown here. And therefore, for an arbitrary function, we can perform a Taylor expansion, and we can compute the value of, I mean, basically we use this formula, sorry, and a Taylor expansion to compute the value of applying the formula over an arbitrary function. And this allows us to recover this for loop value of the Kasparov dimension in the ABJM theory, which agrees with the prediction of integrability for the Kasparov dimension. So we have been able to reproduce this prediction of integrability. And also at two loops, this is consistent with the Feynman diagram computation that was done some years before. So let me conclude. We have studied in the ABJM theory, and for the four-particle case, the result of performing L-1 integrations over the L-loop integrand for the logarithm of the amplitude. In particular, we performed the integrations up to L equals 4. We found an R finite result, which has uniform transcendental degree. And we found that we have to include parity odd terms in the integrated results. We gave a prescription to compute the Kasparov dimension, and we used that prescription to reproduce a for-loop Kasparov dimension of the theory. There is an interesting simplicity of the leading singularities of the integrated results, and we found some interesting sign patterns in the Euclidean region. So, future directions. Well, one open question is to understand the relation of the integrated negative geometries with Wilson loops with Lagrangian insertions. This is well understood in Forsby and Mills. Basically, yes, that the integrated negative geometry can be obtained from a Wilson loop with the Lagrangian insertion. But in ABJM, this relation is a bit more subtle and has to be better understood. Another question is to go to higher points, to go to a 5-particle case and to a 6-particle case, for example. Well, to a 6-particle in ABJM, because the 5-particle amplitude in ABJM is quite is trivial. Also, an interesting question is to generalize to even further higher loops, and maybe to use a bootstrap analysis for doing that. Also, it would be interesting to sum some diagrams non-perturbatively, as it was done by Hen, Kahneman, and Trinka. And to understand, for example, how to compute the last loop integration that steps in the way between the integrated negative geometries and the full amplitude. Okay, so thank you very much.
Great, thank you, Martin. We can give. I was looking for that. Yeah, claps.
Okay. Any question?
Should we stop recording or do this question in Spanish?
Yeah, so we can ask in Spanish.
Okay. Okay. I will stop here.